Hello students and welcome back to my channel. Today we'll be discussing the different aspects of Young's double slit experiment exclusively for board exams, that is class 12th exams. Okay. So without wasting time, let us discuss them. Now, in Young's double slit experiment, basically we study the superposition of two waves which are coming from two coherent sources, and the effect is observed on a distant screen. Okay, so let us see the diagram. So first of all, see, the diagram will be something like this. See, so first I'll draw a slit here. Okay, so this is a slit, and so this we have a slit. Two slits are there, you can see. You can name them as slit S1 and S2. Then you have a central line. I'll draw the central line here. Sorry, so this is not very good. So I'll redraw it. Yes. Okay. Now I'll call the midpoint of the slits as C. Okay. And then also I'll draw a screen, distant screen, you can see, and this point I'll mark it as O. Later we'll see that this is known as central bright fringe. Central bright fringe. We'll see this, don't worry. Alright, now somewhere you have an actual source here and equidistant from both the slits, that is S1 and S2. So basically what will happen when light comes out from source S, then you'll see that from here and then from here the light will start appearing this way. Dotted lines represent the crests and drops, and continuous lines represent the crests. So this will alternate crests and drops. So they'll interfere here. That is this way. They'll undergo interference. Okay. So now it is important that in interference the frequencies must be same. It's very, very important. So that means if frequency of the wave coming from source S1 is F, then that coming from source S2 should also be F. As you can see, S1 and S2 have been derived from the same parent sources. So such sources are known as coherent sources. And incoherent sources is absolutely duplicate of each other. They'll be, they'll be emitting waves of same kind without any phase difference. Probably there could be phase difference also, but when in these kind of situations, the phase difference between them will be zero, and of course they will be emitting light of same frequency. So now here, as the waves superimpose, they undergo superimposition here. This position could be a bright fringe, or that point could correspond to a dark fringe, or it could be of intermediate intensity as well. Okay, right. So here our duty is to know or ascertain the positions of dark and bright fringes. As we will see that there will be alternate dark and bright fringes, and the intensity will vary with a certain pattern. Those things we'll see. So let us select a point P on the screen, say at a distance of Y from the point O. Okay, right. Now here two things you have to understand very, very clearly. First is the distance between the slits is small d. Distance between the plane of the slits and the screen is capital D, and the wavelength of the light coming out is lambda. So here first thing is lambda is of the order of few micron, 0.4 micron to 0.8 microns visible light, students. Small d will be of the order of 1 millimeter, and capital D will be of the order of 1 meter. So based on this, you can very clearly see that lambda is too small compared to small d. Similarly, small d is too small compared to capital D. These conditions are very, very important, students. You have to realize. Otherwise, perhaps we may not be able to get the interference pattern there. Okay, so for successful observation of interference pattern, these conditions are necessary. Right. So now here our aim is to know the nature of this point B, whether it is bright or dark or whatever it is. Okay. In fact, we'll be locating the positions of dark and bright fringes. So for that, you know that the intensity, okay, of the resultant intensity will be dependent on the path difference or phase difference, because both are interlinked with each other. Okay. So let us first decide the path difference between them. So coming to path difference between the interfering waves, path difference between the interfering waves is, I'll denote it by delta L. Okay. So this is nothing but the difference in optical paths between the interfering waves. Okay. For air or vacuum, the optical path is equal to the geometrical path. So for the wave coming out from S2, you can see source S2, the geometrical path length is S2P. So that will be the optical path. Similarly, for the light wave coming from S1, you can see S1P is the geometrical path, which will be equal to the optical path. So difference in optical path is known as the phase difference, which is here equal to geometrical path. Okay, right. Then now I'll take this, I'll keep it as equation 1, not a problem. Delta, I'll replace it by delta. Now you see, from triangle, I'll drop two perpendiculars, okay? One perpendicular from S1 onto the screen, I'll name it as M, and another perpendicular from S2 onto the screen, I'll name it as N. So from triangle PS1M, you can see PS1M, this triangle. Immediately we can write that hypotenuse square, okay, is equal to, I'll write it as S1P whole square, okay. It's one and same, of course. So S1P whole square is equal to capital D square plus PM square, which is equal to capital D square plus Y minus D by 2 whole square. Remember, students, this is D by 2. Similarly, this is also D by 2. So from Y, if we deduct D by 2, we'll get PM. So this I'll number it as equation 2. Similarly, from triangle PS2N, this triangle PS2N, we can write S2P whole square is equal to D square plus PN whole square. Okay, students. So which I can write it as D square plus Y plus D by 2 whole square. You can see from the figure, students. This PN is equal to, from here to here it is Y, PO plus ON, that is D by 2. Now let us subtract equation 2 from 3, that is equation 3 minus equation 2, because we require S2P minus S1P, so I am subtracting this way. So this will get cancelled, students, and here we'll be left with, you can see A plus B whole square minus A minus B whole square will be 4 times AB. Okay. Also, if we apply the formula A square plus B square into is equal to A plus B into A minus B. So A plus B into A minus B. So this is around 2 YD. Now you can see, students, try to understand this. The very important thing I'm telling here, we are, the underlying assumption is point P is close to the central bright fringe. Very important, I'll tell. Since point P is close to the central bright fringe, that is O, so therefore we can write S1P or S2P roughly equal to capital D. Just imagine, students, this distance is in millimeter, maybe half a millimeter or 1 millimeter or something like that, whereas capital D is thousands of millimeter, that is 1 meter. So needless to say that S1P will be more or less same as S2P, which in turn will be more or less equal to capital D, for the simple reason that point P lies close to point O. So I'll approximately write this as D plus D. And this is the required path difference, students. You can see path difference. So therefore, finally, I can write the path difference as Y small d by capital D. So this is the formula for path difference for the interfering waves at point P. Okay. Right. Now, depending on the path difference, okay, point P, the position of point P could be bright or dark. We are only interested in dark and bright fringes, students, not in the rest of the fringes. I mean, we have only dark and bright fringes. The other portion of the screen will have average intensity, okay, or intensity in some medium range, and that is of no value for us. Right now, we are interested only in the dark and bright fringes. So next we'll see positions corresponding to bright fringe. Okay, position corresponding to bright fringe. Now, as we know that in order to have bright fringe, the type of interference which should take place there will be a constructive interference. In other words, we have to explore the condition for constructive interference. Constructive interference, where the two waves enhance the effect of each other. They support each other and hence they enhance the effect of each other. So for that, we know the path difference should be either 0 or 1 lambda, 2 lambda, 3 lambda, of course plus or minus, but okay, plus or minus, both, plus, minus, both. Okay. So accordingly, we can have, if it is plus, then certainly point P will lie above the central line. You can call this as central line, students. Whereas if path difference is negative, that means P is somewhere below the central line. That is the only difference. Alright, so next, so in general I write n lambda, where n belongs to integer, So I can write the path difference corresponding to the nth bright fringe is this. So therefore I can write the nth position corresponding to nth bright fringe is lambda capital D, n lambda capital D by small d. Okay, you can go on putting n equal to 0, 1, 2, 3, etc., etc. Now as a note, you can see when n is equal to 0, clearly y is equal to 0. So this marks the position corresponding to central bright fringe. So that marks the position of central bright fringe. Okay. Also it is known as fringe, bright fringe of zero order. Also it is known as zero order fringe, because zero order fringe is possible only in bright fringe, zero order fringe. Okay, right. So if you go on putting n equal to 1, 2, 3, 4, then you will get like this. See, y0 is 0, then y1 will be, as you put n equal to 1 here, 1 lambda capital D by D. Then the position corresponding to second bright fringe is this. Then the position corresponding to third bright fringe is this, and so on. Okay. As you can see, that the distance between any two consecutive bright fringes is exactly lambda capital D by D. That means y1 minus y0 will be same as y2 minus y1, which in turn will be same as y3 minus y2, and so on, which is equal to lambda capital D by small d. Okay, I'll show these all these things on the diagram, don't worry. Right? All right. So then moving on to the corresponding, positions corresponding to dark fringes, we'll see. So next we are going to explore positions corresponding to dark fringes. So as you know, dark means what? Absence of light. Dark represents absence of light. And if the intensity of light is poor or weak, so that means basically there is the kind of interference taking place is known as destructive interference. So kind of destructive interference is taking place. So we have to explore the condition and hence the position corresponding to destructive interference. So for that we know path reference should be equal to odd multiple of lambda by 2. So 2n plus or minus 1, anything is okay. Lambda by 2, where n belongs to integer. Okay. N belongs to integer. Integer means you have to start from 1 if you are taking 2n plus 1. 2n minus 1. If you are taking 2n plus 1, then n can start from 0, not a problem. So let us take it as 2n minus 1 lambda by 2. So n will start from 1, 2, 3, etc. Okay. So if you equate this to yn small d by capital D, so then we'll have the position corresponding to the nth dark fringe is odd number by 2 into lambda capital D by small d. Okay. So this is the position, students. So putting n equal to 1, we get y1 is equal to 1 by 2 into lambda capital D by small d. Similarly, putting n equal to 2, we can write y2 as 3 by 2 into lambda capital D by small d. Similarly, putting n equal to 3, we can write y3 as 5 by 2 lambda capital D by small d, and so on. So here you can see there should be an odd number. Now similarly, so these mark the positions corresponding to dark fringes. Now separation between any two consecutive dark fringes. Consecutive means adjacent, neighboring, that is next to each other. Consecutive dark fringes will be how much? This minus this, that is y2 minus y1 or y3 minus y2, whatever it is. Again you will get lambda capital D by small d. Because from 1.5 times if you deduct half, you will get 1 times of lambda d by d. Or 2.5 times minus 1.5 times is again this. So that means all the dark separations are dark fringes are equally separated from each other, and similar is the situation in case of bright fringes as well. So this is separation corresponding to any two adjacent bright fringe. Okay, that's it. So this is clear, students, I hope. Now let us see the diagram which clearly indicates the positions of different dark and bright fringes. Let us try to understand the diagram. So I'll draw the diagram here. So first of all, this is the screen. Okay, and this is the central line. I'll draw the central line somewhere. Now this side there will be slits which I am not showing students. We don't want to know this, okay? The position of the slits. Yeah, slits will be there of course. Now this is the position corresponding to central right fringe y equal to 0 because this, let us say this is y axis and this is x axis. Okay. Now you can see for dark fringe, first let us what you say mark the dark positions corresponding to dark fringes. Dark fringes are visible if we use, or let me use some dark color. Okay. So if I take, for now if I take lambda d by lambda capital D by small d as beta, I can write this as beta by 2. Okay. So this position is at a distance beta by 2. Then the next is 3 by 2 beta, 3 beta by 2. So the next position of dark fringe is 3 times beta by 2 and so on. Next one will be 5 times of beta by 2 at a distance 5 by 2 and so on. Now similarly, let us come to bright fringes. You can see students, in case of bright fringes, the center bright fringe is there of course, okay, O. Other than that, the first bright fringe is at a distance beta. I have taken this as beta, remember. So beta, 2 beta, 3 beta and so on. So here we have beta. This marks the position of first bright fringe. Then you have 2 beta, which marks the position corresponding to the second bright fringe and so on. Okay students. Now you can see that as you move from the central bright fringe, the first thing you will encounter is a first dark fringe. This is the position corresponding to first dark fringe. Then as you move away and away from the central bright fringe, you will be encountering the first bright fringe, then the second dark fringe, then the second bright fringe and so on. Okay. So this is how you will be getting. Similarly, as you move down the central line, same thing will happen. Okay. All right. Now students, if you see the screen, probably the screen, this will be white, then this will be dark, then again this will be white, this will be dark again and so on. Now as far as the intensity of light is concerned, as you move from here, let us say one of the position of bright fringe, you have to reach here so that the pattern of variation of intensity repeats. Here you see intensity goes on decreasing, it becomes a dark fringe, again it increases. Okay, so here again you can find a maximum intensity. Here the intensity is maximum and once again the intensity is maximum here. So that means this width is something in which the variation of intensity takes place in a certain pattern and that gets repeated in the next another equal width. So these widths are known as fringe widths. So beta is known as fringe width. That means one complete dark fringe and one complete bright fringe together, adjacent bright and dark fringes together will be called as a fringe, and its width is fringe width, which we had already taken as lambda capital D by small d. Okay, this is the fringe width. Now usually fringe width will be again of the order of millimeter. Okay, practically when you substitute lambda, the wavelength of visible light may be somewhere between 400 nanometers to 800 nanometers. Capital D will be of the order of meters. It can be 1 meter, 1.5 meter, etc. And small d is of the order of millimeter. Then fringe width is also of the order of millimeter. So all these things are this all these things you have to memorize here. Okay, students. So let me finally plot the intensity here, and then probably we can wind up this. Okay, now let us see the intensity. Okay, the intensity will be something like this. See, at the central bright fringe, the intensity will be maximum. Then it will be minimum at the first dark fringe, then again maximum at the first bright fringe, then again minimum at the second dark fringe, and so on. So this marks the position corresponding to first dark fringe. This marks the position corresponding to second dark fringe. This marks the position corresponding to first bright fringe, and this point marks the position corresponding to second bright fringe. This is the position corresponding to central bright fringe, and so on. Okay. If you recall, students, we have already discussed the intensity variation and all. Okay. So if here the intensity will be 4 times of I naught, whereas here in the dark fringes the intensity is 0. Minimum intensity is 0 and maximum intensity is 4 I naught, where I naught is the intensity due to each slit, where I naught equal to intensity on the screen at any point on the screen due to each slit. Okay, so that is clear, I hope, right? Now, just as a small note, okay, suppose this is the screen. This is the screen, and these are the slits. This is the central line, student. This is the central line. Now P is a point here. If you can find the path reference, we have already found the path reference, then you can find the phase difference as well, isn't it? Then assuming the intensities of light, equal intensities of light coming out, the resultant intensity we know it is 4 times of I naught into cos square of delta by 2, where delta is equal to phase difference between the interfering waves. Phase difference between the interfering waves. Okay, and we know delta, that is phase difference upon 2 pi, is equivalent to delta L upon lambda, where what is delta L we saw? Delta L is basically y small d by capital D. This is small d, students. This is small d and this is capital D. So based on this, you can substitute the value of delta L here and find delta. Once you know delta, you can use this delta here. Okay. Then next we'll see the conditions which are required for sustained interference. That will be the last topic, students. Then we'll conclude it. Okay. So conditions required for sustained and distinct interference pattern. Distinct interference pattern. Okay. First and foremost is the sources should be coherent in nature. They should be coherent in nature. Sources should be coherent in nature. Now students, if the sources are not coherent, then what will happen? the phase difference between them will not remain same. If the phase difference is between them, between the individual sources doesn't remain same, so naturally the phase difference between the interfering waves will not remain same. So accordingly the intensity will keep fluctuating at the point with time, and the phase variation is at such a tremendous speed that the phase variation, I mean the intensity variation, will also be at the same tremendous speed, so that on an average our eyes will not be able to detect this variation at such a high speed, and we'll have the feeling that the intensity is uniform, that is same, it is not changing, and we'll get the average uniform only, I'm sorry, average intensity distribution, which is simply I naught plus I naught, that is 2 I naught. So everywhere the average intensity will be 2 I naught everywhere. So therefore, if we want to see distinct interference pattern, that is distinct bright and dark fringes, then certainly they should be coherent. Now coherent sources should be derived from a single source. Two independent sources cannot be coherent. So coherent sources should be derived from a single parent source. Two independent sources cannot be coherent because there cannot be any phase relation between the individual waves which are emitted by the two sources, right? Then second, of course, since they are coherent, they are having the same frequency, but still I will write it once again that they should have same frequency. The waves should have same frequency. Same frequency wave should be there. Only then sustained interference will be is possible. Otherwise, there is no question of any interference. So interference itself represents superposition of waves with same frequency. That is very important. These two are very important conditions as compared to other conditions. Okay, students. Then you can see for good contrast. Okay, as seen on the interference pattern, as seen on the screen, that then I mean should be 0, so that there is a good contrast between bright and dark fringes. If dark is perfectly 0, so for that a1 minus a2 should be 0. In other words, a1 should be approximately a2, or I1 should be approximately I2. That is, the intensities due to both the slits or the amplitude should be same. So you'll get a good contrast in the interference pattern. Then also fringes should be well separated, students. So in order to have well separated fringe width, so we can have that beta should be proportional to capital D. Okay, that is, the distance between the screen and the plane of the slit should be more, and also beta varies inversely as small d. That is, the slit separation should be lesser as possible. Then we have full and final condition that the slit width should be small. The slit width should be small, because if that be the case, then what will happen? The sources will be just like point sources, and we'll have exact interference pattern. Whereas if the slit width is large, let us say I'm showing one slit, you can see width is large, then you can imagine several points on the slit width. So this wavefront, different points on the wavefront themselves act as sources as per Huygens wave theory. So different wavelengths will start interfering, and then it will be more of a kind of diffraction rather than interference. In other words, here the secondary wavelengths, then secondary wavelengths here, all of them will together superpose and they'll disturb the interference pattern. So the interference pattern will not be distinct. That is, the bright fringes will not be distinctly separated with dark fringes. Okay, so therefore the slit width should be as small as possible. Okay, students, right. Next we'll be seeing certain questions, students. Quickly let us discuss certain questions. so that then we'll wind up. Okay, so just for your class 12th board exam I am discussing, not nothing very difficult questions. I have chosen very simple questions. All right, right. So in a YDSC students, the fringe width is 0.2 mm if the wavelength of light used is increased by 10% and the separation between slits is also increased by 10% and the fringe width is. Now students, we studied that fringe width is lambda capital D by small d. Okay. Here the slit separation is small d, whereas the separation between the plane of the slits and the screen is capital D. So if this is increased by 10%, so it will become 1.1 times. This is also increased by 10%, it will also become 1.1 times. So the factor of change for beta is still 1 because the ratio capital D by small d did not change. Even though individually capital D and small d changed, but their ratio did not change. So beta will not change. So no effect on beta. So beta will remain same, students. Coming to question 2. If the sodium light in YDSE is replaced by red light, the fringe width will. As we all know that fringe width is lambda capital D by small d. So in that case, what will happen? We can say that fringe width will be proportional to lambda. Fringe width is proportional to lambda. So now, as you know that sodium light, the wavelength is somewhere around roughly you can say 5900 angstrom. Whereas for red light, the value of lambda is somewhere around 3900 angstrom. Sorry, I'm sorry. 78. You can take it as 78 degree angstrom. So basically, we have replaced less lambda with more lambda. So beta will increase because beta is proportional to lambda. So if lambda is increased, beta will also increase. So the fringe width will increase. Then moving to the next question. Question number 3. In an interference experiment, third bright fringe is obtained at a point on the screen with a light of 700 nanometer. What should be the wavelength of light source in order to obtain fifth bright fringe at the same point? So this is the screen, students. This is the central line. Then now you have a point here. Okay, it's clearly given third bright fringe. So third bright fringe of 700 nanometer is obtained there. And what should be the wavelength in order to obtain fifth bright fringe? So if we can have fifth bright fringe of some new lambda which we don't know corresponding to the same position. So this should be same, student, for both. So if this distance, okay, this distance should be 3 times of beta for this, and this distance should be 5 times of beta for this. Okay, I'll take the new beta as beta dash. Are you getting the point? Because from central bright fringe, as you move one beta distance, you will be getting the first bright fringe. Then you move another beta, you will be getting the second bright fringe. And as you move the third 3 beta, you will be getting third bright fringe. So as you move a distance n beta, you will be getting nth bright fringe. So here we require fifth bright fringe. So we have to move a distance 5 beta dash. So I can write 5 beta dash is equal to 3 beta. And you know beta is equal to lambda capital D by small d. Remember capital D by small d is same. The setup is not disturbed or not changed. So I can write beta is proportional to lambda. So I'll replace this by this. Okay. So 5 times of lambda dash is equal to 3 times of lambda. Lambda is how much? 700 nanometer. So therefore lambda dash is, I'm sorry students, lambda dash is 3 sevens are 2100 upon 5. Now if you multiply and divide by 2, so basically you will get this. Okay, right, 420 nanometer. In a YDSE, 12 fringes are observed to be formed in a certain segment of the screen when light of wavelength 600 nanometer is used. If the wavelength of light is changed to 400 nanometer, number of fringes observed in the same segment of the screen. Now let us say this is the screen, students. This is the screen. I'll use this. Okay, suppose this is the screen. Now it is given that 12 fringes are found when light of wavelength 600 nanometer is used. Now suppose this is one fringe width, then this is another fringe width. So this is one fringe width, this is another fringe width, and so on. So this way, let us say the width of the screen is B. Okay, and here we have suppose nth bright fringe. So this entire width will be n times of beta, where beta is the fringe width. I hope that is clear. So this remains same because the screen is same. So in the first case, number of fringes is 12. Okay, beta I can replace beta by lambda. Lambda is 600 nanometer. Lambda capital T by small d. Remember, capital T by small d will get cancelled. Don't worry. Okay, then is equal to the new number of fringes we have to find corresponding to a wavelength 400 nanometer. So this will be 400 nanometer into capital D by small d. Okay, so capital D by small d gets cancelled here, and we are left with 4 3s. Okay, so 3 6 18. So n is equal to 18. 18 is the answer. Then coming to question 5, and an interference pattern was made by using red light. If the red light is replaced with blue light, the fringes will become. As you know, fringe width is directly proportional to lambda, isn't it? So if we replace red light has approximately 800 nanometer, whereas blue has approximately around maybe 400 nanometer. Approximately, students, it is enough. So we have replaced the more wavelength with lesser wavelength. So if lambda has reduced, beta will reduce. Okay, so fringe width will reduce, means fringe will become more narrower, fringes will become narrower. Then Young's double slit experiment is performed with light of wavelength this month. The separation between stages and the screen is present. What is the distance between consecutive bright or dark fringes? Now they are asking the fringe width. They are simply asking the fringe width, and fringe width is lambda capital D by small d. So let us substitute the value. Lambda is how much? 550 nanometer. Nano means 10 power minus 9. I am substituting everything in SI unit, students. Then capital D is 1 meter, and small d is 1.1. That is, you can call it as 11 by 10 millimeter. Milli means 10 power minus 6. So we'll be getting the answer in SI unit. So as you can see, 1150s. Okay, and this 10 goes up. So this 10 goes up, and here already there is a 10, so 10 power 2. Here we have 10 power minus 9, and this 10 power minus 3 goes up, becomes 10 power plus 3. So we have 10 to the power minus 9 plus 5 is minus 4 meter, which I can write it as 0.1 millimeter. So none of the options are correct, students. We have to be very careful, students. Okay. No. I'm sorry. 5. I have missed 5. I'm sorry. 5 I have missed. This 5 is there. So 5. Okay. So 0.5. C option will be the correct option. So this is 5 upon 10 millimeter. So 0.5 millimeter. Then question number 7. What will happen if a torch is used in place of monochromatic light in Young's interference experiment? Now students, here basically torch is basically emitting light of a mixture of wavelength. Several wavelengths will be having simultaneously being coming out of the torch. So if we have several wavelengths, so each wavelength will have its own interference pattern, and the dark fringe of one will overlap with the bright fringe of other, and so on. So the entire pattern will get disturbed. Then it is best to say that no fringes will appear. See students, distinct fringes will appear if and only if the bright fringes are well separated from dark fringes, and similarly the dark fringes are well separated from bright fringes. Whereas here dark of one color is overlapping with the bright of another color, so what is the use? there won't be any clarity there. So it's simple to say that no fringes will appear. So D option. Coming to question 8, in YDSE, one slit is covered with a blue filter and the other with yellow filter. Now here you see, student, both the sources do not have the same wavelength, because the slit which is covered with the blue filter will start emitting blue light. So blue light has its own wavelength, maybe perhaps let us say 400 nanometer. Then the other slit is there which is covered with a yellow filter, so it will start emitting yellow color. Probably yellow color has a wavelength somewhere around probably maybe 600 nanometer approximately. So if wavelengths are different, frequencies are different. And in the beginning we studied that interference means it's very very necessary that frequencies must be same. If frequencies is not same, then the fringes will not be sustained fringes. That is, the same point will be dark, bright, and so on. And the fluctuation will be at such a rapid rate that our eyes will not be able to detect that variation because of the natural limitations. So basically we say the interference pattern will not be found because interference will not take place actually. Then YDSE is performed in air and then performed in water, the fringe bit will. Now students, again the same thing, beta is equal to lambda capital D by small d. Now since capital D by small d is same, it is constant, we are not disturbing the experimental setup. So I can say beta is proportional to lambda. Now what happens when the entire setup is immersed in a liquid water? Lambda will reduce. Lambda in water is equal to lambda in air upon mu. Since mu is more than 1, certainly lambda in water will be less than lambda in air. So since beta is proportional to lambda, we can say the corresponding fringe width will also reduce. Corresponding fringe width will reduce. So therefore, the fringe width will decrease. Then coming to question 10, this should be question 10, students. In a YDSE, the fringe width is found to be this much if the whole apparatus is immersed in water of refractive without disturbing the new fringe width. So certainly the new fringe width will be the initial fringe width upon mu. Just now we saw. So the initial fringe width is 0.4 millimeter, whereas divided by mu means into 3 by 4. So 4.1, so we have 0.3 mm. Okay, so A option is the correct answer. Then coming to question number 11. In a YDSE, a glass plate is placed before a slit which absorbs half the intensity of light under this situation. Now since students see initially the intensities were same. Okay, as I told you, unless otherwise mentioned, we have to always assume that the intensity is same for both the slits, identical. So in that case, what will happen? The maximum intensity will be 4 times of I naught, and of course minimum intensity will be 0. In the next situation, it is given that it absorbs the half the light intensity. Now you see here one of the thing in, suppose you take this, a slab was introduced and it absorbed half the intensity, means the intensity of light coming out there is only I naught by 2. So now if we calculate the maximum intensity, if you recall, we have already studied this. The formula for maximum intensity is under root I1 plus under root I2 whole square. So root 1 plus root half whole square. Okay. So if you expand this, it will be 1 plus 1 by 2 plus root 2 to I naught. A square plus B square plus 2AB. A square plus B square plus 2AB. So this will be 3 by 2. 3 by 2 is 1.5 plus root 2. Root 2 is 1.414. So approximately this will be somewhere around 2.914. Okay. Whereas here what it was 4 I naught. So certainly the maximum intensity has reduced. Similarly, minimum intensity, you know the formula is under root I1 minus under root I2 whole square. So this will be 1 minus 1 by root 2 whole square into I naught. So it will be 1.5 minus 1.4, and also approximately it is point 0 6 9 0.096 I naught. So it is not, it has increased because initially it was 0. So now let us see what can be the best answer. The brightness of fringes decreases, the fringe width decreases, no fringes will be observed. The bright fringe becomes fainter because intensity has reduced, and the dark fringe becomes of finite light intensity. You can see dark fringe has become certain finite intensity. So D option is the correct option. All right, students. That's all, students, in this video. Thank you so much for watching. Thank you.